Okay, good morning to you all. So before we begin the class, I just wanted to tell you that the assessment, whatever that we are going to do for you people, will be online, right? So there will be a quiz questionnaires that will be shared to you either today or tomorrow. It will comprise of 15 questions, right? You are supposed to answer these 15 questions, right? And there will be a time limit for attempting this course, this quiz, right? You may have to attempt before the date and the time that is being said, right? And after your quiz is done, you will have a series of such kind of quiz starting from now on, right? Where you are required to do an attempt for these quizzes, right? So coming back to where we had stopped in the last class, right? We had completed something about MapReduce applications, right? We had completed something on the case units. How do you do a testing, right? So there were two things that we had suggested in the last class. One, the testing can be done either on a local machine, right, with certain configuration settings and things like that. Second is you can either do a testing on a mini cluster, right? So we had a concept called as mini DFS clusters where the algorithm will run and you can see the output of these algorithm, right? So the testing, whatever that we are trying to do is for the sake of understanding the behavior of the algorithm, whether the algorithm behaves in exactly the same way as what we have coded, what is the output of that particular algorithm, right? So to test these aspects of that particular algorithm, we need to test the algorithm first of all, right? It is as good as you have written a code for we have written a code in the C programming for a bubble sort. Now you have to test it. So how do you test it? So you can test it only when you run the program and give some sample inputs to it and see whether the output, whatever that you are trying to get, is the same as what you have expected it to be. So, in a clustered kind of an environment, it is not as easy as what we say in case of C programs, right? Because you are connected with so many cluster nodes, the behavior of the program in a single node may be different from a behavior of the program when multiple nodes are connected to it. Hence, we are required to do testing at the local level. We are required to do the testing at the mini cluster level, right? Not disturbing the entire cluster of nodes that is available in the Hadoop system. So this is what we had started with. So we had went through both the way of doing the testing in Hadoop, right? And we had started running a test set of classes, right, in the cluster. So we had stopped at this in the last class, right? Now coming back to the next important item, which is the anatomy of the MapReduce job run, right? So what is the anatomy of the MapReduce job run? We have seen similar kinds of anatomy when we had discussed something on writing of a file and reading of a file, right? There were definitive procedures which were connected with writing and reading of this particular files. So similarly, when you talk about running a job of MapReduce in a Hadoop cluster, there is a definitive steps that will be included in it. So what are these definitive steps? So the definitive steps are something like this. The first and the foremost thing is you need to run a MapReduce job. So for running a MapReduce job, you have to submit that particular job to the cluster. So to submit the job to the cluster, you have a call called as submit. So this method takes all the details of the job configurations related to that particular job. It takes the data requirement and other requirements of that particular jobs which is required for processing. All the versions of the Hadoop, starting from Hadoop 1.0 till Hadoop 3.0, incorporates this MapReduce job tracker, which determines the execution of the individual jobs, right? And even in the even in the intermittent implementation, which we see, that is the MapReduce 2.0, which was the previous latest version of the Hadoop, you can see that Yarn was there, which was responsible for doing the MapReduce job run, right? So now the framework, whatever that is being designed in the MapReduce or the Hadoop for the execution of a particular job, the property name is called as mapreduce.framework.name.property. This is the property that will be used for running the job. Okay. So the next important thing is, in a MapReduce version 1, right? There were 4 independent jobs that used to run. What are these 4 independent jobs? The name node, the data node, the job tracker, and the task tracker. These were the 4 important processes that used to run after the cluster is up and running. And this was completely recorded in JPS, right? Job processing schedule command, right? When you type JPS in the Hadoop terminal, you will get to see all of these processes running, and you can also see that JPS is tracking the jobs that is being submitted into the cluster, right? So at the highest level, you've got 4 independent entities, as already being mentioned. The job tracker, which basically does the job of coordinating the jobs between various task trackers, and it is basically a Java application whose main class is job tracker. Similarly, the task trackers are slaves of these job trackers, right? They are a particular job is divided into multiple task trackers, and they are submitted into different data nodes. So again, the task trackers are Java applications which are written, whose main class is the task tracker class. So the distributed file system which you have is used to share the jobs or the files between the other entities. So this is the scenario in case of MapReduce 1. So it typically looks like this. So you have the MapReduce program, which is submitted as a job, right? The first step is you submit it as a job. You run it as a job, right? Now, once when you submit it as a job to the client JVM, right? The second thing which would happen is that job gets submitted to the job tracker. Now, the job tracker, before the job is being submitted to the job tracker, the submit function assigns an ID to it, and that ID is called as the job ID, right? And after the job ID is being given, the job configuration also um, submits a copy of the required resources to the DFS, that is the HDFS. Now, after the job ID is being submitted to the job tracker, right? The tracker will also have a keen interest in looking into the resources which are there in the HDFS system, right? And after the resources and other job ID is being created, the job formally submits the job to the job tracker. That is the resources that is required for running the job ID of it, everything is completely submitted to the job tracker. Now, after this is completely submitted to the job tracker initiates the job. So the job tracker initiates that job. And after the initiation of the job happens, the job tracker picks the input data splits that is required to run for this particular job. And after this is being done, the job tracker is obviously putting all the jobs into the respective task trackers. So every task tracker, whatever that we do, has something called as a ping messages, right? That is, it keeps pinging the statistics of the completion of that particular job. And that statistics of pinging to the job tracker is called as heartbeats, right? So it regularly keeps pumping in its heartbeats into the job tracker, telling that the map task and the reduce task has been completed, right? Or it is being completely working with respect to the the jobs what has been submitted, right? Finally, what happens? It retrieves all the job resources, completes the execution, and returns all the individual tasks back to the job tracker. Now, it is the work of the job tracker to put these pieces together as a single output and submit it as the final output. So this is the anatomy of how a MapReduce job runs in case of classical framework like Hadoop. So this is the flow again, right? The flow again is a detailed flow of how the job submitter does this, right? And what are the specifications of the job, right? How are the input splits computed for that particular job, right? If the splits are not computed for a particular job, then it doesn't turn out to be a MapReduce program. So this is a very important aspect of the MapReduce program, right? Now, next, the resources that is required for completing the job, right? You can see that even in a single C program, the resources that may be required, a very simple program, taking an input from the user and printing it on the output screen. Now, in this particular scenario, the resources that are required are the input system, that is the input resource system, then the output resource system. These are the two things that are essentially required as a resource for this particular program. So similarly, when you are talking about any program that is that is to be that is to be executed, right? There are certain requirements for execution, right? These are computational requirements that includes resources, that includes other dependencies that are required for that particular job to run, right? Now, when a job is being run or job is being submitted, it is submitted as a jar file to the execution system, right? You know that you cannot just submit a .java file and execute that .java file as we commonly do with all the programming aspects of programming languages. So Hadoop cluster is quite different when compared with the other execution systems. So the job submission is a jar file that you are submitting into the cluster. So when you are submitting a jar file into the cluster, right, which is submitted to the JVM of that particular name node, right? There is an insurance that is going to be made by the client JVM that there is a replication factor that is included into it. Now, this replication factor, what it basically does is it replicates the resources that is required into another node. It replicates the details of the job into the secondary name node as well as certain replication nodes. So this is the work of that particular replication factor, right? And after all of these things are done, now we are ready to go for the submission of that particular job. So the first step is the job initialization. What are the prerequisites that are required to do the job initialization aspect of it, right? Now, once when a job tracker receives a call to do submit, it puts everything into the internal queue where the job scheduler can pick it up and initialize it. So the initialization is just preparation of the memory, preparation of the creation of objects, right? Preparation for the job to be executed, right? These are some of the preliminary setup that is being done before the job gets into action, right? So it encapsulates the job information, the task information, the bookkeeping information. Now, the bookkeeping information is nothing but the record information of that particular job. What is it exactly trying to do? What are the steps that are there in that particular job? So these are the progress monitoring aspects which is associated with that particular job, which is encapsulated along with the tasks what is being individually created by the job tracker, and also the record of that particular task. What is it trying to do, right? So this is how the first step happens after the job submission is done, right? Now, the next is it creates a list of tasks that is to run and the scheduler associated with that particular job. and also the input splits that are retrieved from the job resource unit, right? So these are the three important things that matters a lot in the in that particular system, right? And after this is being done, the job tracker essentially creates the input splits, right? After creating the input splits, it basically creates the number of reduced tasks, the number of map tasks, right? You should know that you already are aware that the number of reduced tasks will always be less than the number of map tasks. You are very well aware of this particular scenario. Now, even then, that there is a property in the MapReduce system where in which you set the number of reduced tasks, right? You set the number of reduced tasks that are associated with that particular system, right? This is the job initialization factor of, or the steps involved in the job initialization. So the next important thing under the job initialization is how many map tasks has to be created and how many reduced tasks has to be created, along with the job setup task, right? The process that is responsible for setting up the task, and the job which is responsible for cleaning up the task. Now, this is a very important information. The reason is because, right, every job that executes, there should be a garbage collection system which will basically take care of cleaning up that particular job. Right, there will be several intermittent files that would be created during that particular process, and it is very important that after the completion of the job is being completely cleaned up, right? There would be a lot of logs files that would be created in between, right? And all of these log files that we are trying to talk about basically has uh, a lot of issues, right? That they occupy so much of space and other things in the input, right? This is very important that we reduce it. Right now, how do we reduce it? It is basically up to the job cleaner task to ensure that it cleans up all particular tasks, right? And then you have got something called as output committer class, right? Now, this output committer class is basically into the configuration of the job and determines the code to run. And by default, it has this particular class, which is called as file output committer, right? So this file output committer is responsible for committing the committing the output of that particular program what is being created, right? Similarly, there is a job setup task which will be basically create the final output directory, which will create the temporary working space of that particular task output. Then the final job task, as we cleanup task, as we know, it will clean up all the temporary working space. It will clean up all the aspects which were intermittently used in that particular system. So the second important step is the task assignment step. Now, in a task assignment step, you basically run the task, right? So to before you have to run the task, you should make sure that the tasks are available, right? Now, how the tasks are made available, the job tracker should basically create the number of task trackers. The number of task trackers may be equivalent to the number of data nodes that is being created for it, or it may be the number of task tracker which may be more than the number of data nodes that are created. Now, this task tracker, once when it is being created, it should be regularly checked with, right? It should regularly, periodically send its status. It should send the heartbeat to whatever that is trying to do to the job tracker. If it doesn't send this, then probably the main issue that arises is the survivability of that particular job tracker or not. Whether the task tracker survives or it doesn't survive. This becomes the second important question of the task tracker assignment. Right? So every task tracker that is being created is basically tagged onto the job tracker associated with that. Right? It is one is to many relationship. That is, one job tracker has got many task tracker. However, that particular task tracker has only one job tracker associated with it. It is not M to N relationships. It is from a job tracker, it is one to many. From a task tracker perspective, it is one to one. Right? One task tracker is associated with only one job tracker. It cannot be associated with multiple uh, job trackers. Now, the task tracker's duty is it should create the map and reduce tasks. Right? Like as I already said, the number of map tasks should be greater than the number of reduced tasks. So the task tracker is to make sure that it creates the map task first, and then it creates the associated reduced task for it. So to choose the map task or to choose the reduced task, the criteria that is used is for a map task, the criteria used is the input split that is being given as a resource to that particular system, right? For a reduced task, the criteria for selecting the reduced task is primarily based on the number of intermittent input splits or the number of intermittent output splits that are being created as an outcome of the map task. So based on this, the number of reduced tasks will be created. But it's quite obvious that once when a number of map tasks are created, let's say that there are 4 map tasks that are being created, it is quite obvious that the number of reduced tasks that is going to be created is 1 less than the map task. That is a maximum bound. So if it is 4 map tasks, the number of reduced tasks will be 3 for it, right? So this is how the system basically works in case of the Hadoop system, right? So then you can also see that the number of task trackers, the number of map task under the task tracker, the number of reduced task under the task tracker will be continuously beamed, will be continuously beaconed to the job tracker. So the job tracker will be aware of the minute details of the task tracker, which is the number of maps that are being created and the number of reducers that are being created. Right? With this, so you can see that the task assignment step of this particular program will be completed. Right? And then there is data locality. Right? As I said, data resources are required for the task tracker's execution. Now, the data we have seen in the previous case, in the previous unit, the data transfer can be something like the data local, the rack local, or the data center local, where the data is shared between different data centers, right? So this is the very important task of the job tracker, right? That is, that task tracker basically has to co-locate where the data is available, whether the data is available locally, whether the data is available in the rack, or whether the data is available elsewhere. So it has to basically find out where the data is basically available, right? That is the job of it. So you know that the ease case, the optimal case is where the data local is in the same node, right? We have seen the different scenarios in the last class, last unit, where we have seen the data can be in the same node, can be in the same rack, which is basically termed as rack local, can be between racks of the same data center, or at the end, it can be between 2 different data centers which are geographically located elsewhere. So these are the different scenarios of the data, whatever that we are trying to talk about. So the next thing here is the execution of tasks. Now, whatever that we have done so far is we have created the requisite environment for the execution of the task. We have not actually executed that particular task. Whatever that was required so far was collected and it was initialized in the system. Now, the next step of doing it is you are supposed to make sure that everything goes well, right? You are supposed to make sure that the data, whatever that we are trying to see, is completely under the hand of the task execution, and the task is able to run on its own, right? So for doing this, the distributed cache is needed. The files are to be distributed in different local file system, and also a very important aspect is the task tracker is the one which will do the unjars. That is, the jars which are submitted to the cluster is completely taken out by the task tracker. So the task tracker creates an instance called as the task runner, which is basically responsible for running the task. So the task execution, the task runner is launched on the JVMs, right? And after it is being launched onto the JVM, you can see that the task progresses very well, and it's an amicable interface between the child process and the parent process, right? Once when the task is completed, it starts with the execution of it, right? It starts with the cleanup action of it, which is basically used for making sure that everything is being cleaned up before it goes out of the system. These are some of the very important things which are required whenever we are trying to talk about um, the task execution. Now, when a issue comes in between, that is, there is some issue, and you are not able to ensure that the program does well, then this is the time when the system basically aborts, right? And all the duplicate tasks which are being created, it is basically committed, and the original task which is being uh, running, which has been running so far, um, will be uh, will be deleted off, right? Which will basically ensure that it is aborted, right? So these are some of the preventive measures, right? Instead of having a part of the entire result or a breakup of the entire result, it is very important that we have the required data, what is required for that particular job. So you can see the other part of it. You know that Hadoop is very well good in streaming of the data. It does very well in the streaming of the data, right? You can see that the task tracker and the JVM, whatever is the child process that we have created, is very well going on well with the task tracker, right? You can see that the streaming process can pump in the data that is required for the MapReduce tasks. You can see that the streaming process can give the standard in, standard out values that is associated for that particular job, right? Similarly, you can also see that on the other side, the pipe related data execution, right? In your previous unit, we had completed how streaming data is to be handled and how data from pipes are supposed to be handled, right? Both of these scenarios we had basically went through in the previous example, that is the weather monitoring, weather calculation, that is a max temperature calculation example. We had completed the program both in the streaming way of doing it as well as doing it in terms of pipes, right? You must remember that we had done with respect to unique pipes, and we had also done with respect to Hadoop streaming system, right? We had completed both scenarios of it. So I will pause here for a moment so that you can take a snap of this, because this is a very important slide. Okay. So now when it comes to the progress of that particular job, progress of the MapReduce jobs, right? Um, the progress of the jobs can be, and the status updates is basically through the task tracker. Now, how this is done, you're already aware that the you're already aware that the MapReduce takes the job progress from the tasks that are being executed. The task trackers basically keep zooming in, right? Basically keep beaming in the heartbeats, right? These heartbeats are the essential ways of checking how the data is being flowing, right? That the progress data is flowing, right? So this is one of the ways to understand the task progress, right? How the task is progressing, right? And how the number of map jobs and the reduced tasks are basically working with respect to that particular case. So the propagation of the status updates are something like this. The status updates are propagated in this way, right? It is bottom up approach in the progress that are being updated, right? You can see that from the map task, the task tracker keeps doing the heartbeat. It goes into the job tracker, right? Once when the map reduce tasks basically asks for the status update, the job will basically run a method called as get job status. Now this job status is submitted to the job tracker. The job tracker basically opens up, right, and basically finds out what is the progress of that particular work that is being submitted to the task tracker. So this is the propagation of status update. You can see that the status goes from here, that is a task tracker, up to the job tracker, and the client side application of it, which is getting the status of what is the job, how it is being completed, is what you can see at this particular place. Now, once when a job is being completed, there are several things that happens after a job gets completed. What are those? The first and the foremost thing that is done is that the status of the job is changed to successful, right? The job becomes successful now. The second important thing which happens here is all that processes that were waiting to print that there is a successful completion of the job endlessly waits for this particular method called as wait for completion. Now, once when the wait for completion method is being highlighted, it ensures that the job statistics, the counters, and the other important things are submitted, and you are good to go with respect to whatever that is being printed. This is what happens after the job gets completed. So the job tracker will help you to put up this status of the job even on the HTTP job, right? You can see that there are two ways of viewing the job, right? One way of viewing the job is on the command line, right, where it prints the uh, data, where it prints the progress of that particular map and reduce task. And the other way of viewing data, let's say that your rack server is remotely located, you have submitted the job remotely. Now, once when you have submitted your job remotely, you need to see the progress. You may not be able to see that through the command line. So the other alternative way of looking into it is through uh, this HTTP job notification, right? You will be able to see the output of that particular job during this HTTP job, right? You can see the output from that place, right? So once when the job completion has happened, as we already know, right, the job tracker cleans up all the work, does a cleanup work, and instructs the task tracker to do the same. Right? This is what basically happens once when the job tracker is completed. So in a MapReduce 2.0 kind of a system, the system has something called as yarn, which is basically the resource manager. Now in the MapReduce 2.0, the large number of clusters are supposed to be managed. That is, you may have clusters with size of 4,000 nodes, right, or higher number of nodes, right. In a MapReduce 1.0, the management is very, very difficult if the number of nodes are more, right. You will not be able to complete that particular job with so many number of high number of nodes in a MapReduce 1, right. So yarn, which was initiated in MapReduce 2, is basically yet another resource negotiator. The expanded form of yarn is nothing but yet another resource negotiator. This is the work of that particular yarn. So the yarn remedies is basically scalability of classic MapReduce by splitting the MapReduce into the job trackers into separate entities. So this is the work of the job tracker. Okay. So yarn has two different roles into two different daemon roles. What are those? The first role is the resource manager to manage the resources, right, in the cluster. The second resource is the application manager to manage the life cycle of the application. So um, these are the two important daemon servers or daemon processes that the yarn basically executes. So after the execution of this particular yarn, right, you can see that the node manager running on the cluster node ensures that the application does not uh, make sure that the application does not use enough resources that is allocated, right? The job tracker, for instance, is an instance of an application. Here, the MapReduce jobs are dedicated to each MapReduce masters, right? These are some of the examples of how yarn deals in MapReduce 2.0. So MapReduce on yarn involves more entities than the classic MapReduce. What are the items that it basically involves? It involves a client that submits the MapReduce job. It involves yarn resource manager, which coordinates all the resources on that particular cluster. It also has a Yarn's node manager, which basically launches and monitors the containers where the execution is happening. It also has a MapReduce application master, which is responsible for coordinating and running the tasks. It also has the MapReduce master, which runs the task in the containment unit under the resource manager and the node manager. It also has the distributed file system, which is responsible for sharing the job files. So these are some of the things that basically the yarn, the MapReduce 2.0 basically has. So this is the anatomy of how a yarn basically works, right? So I would pause here for a moment, right, and ensure that you take a snap of this particular slide because this is again very important. Okay, going further ahead with whatever that we are trying to deal with, right? You can see here that the yarn way of initializing and the way of working with respect to the Hadoop cluster is something like this, right? The first and the foremost thing is the client JVM node, right? You can see that it submits a job for running. The second is the job submission here does not happen to the task tracker directly. Rather, it happens to a resource manager which is under the yarn. You can see the difference very well from the previous example to the example what we are seeing today, right? So the resource manager, which is the part of the yarn, will take care of the application that is being submitted. Second thing here is the job basically submits the resources, whatever that is supposed to be required for that particular job, into HDFS. Now, the link between the resource manager and the HDFS is through this node manager. Remember that the node manager as well as the resource manager are the entities of Yarn. They are responsible for starting that containment unit, and this containment unit, which has the node manager and the MR application master, initializes the job and gets the required input splits from the shared system, right? When you type the command JPS in case of MapReduce 2.0, you will not see 4 processes here. Rather, you will see 7 processes. What are those? Name node, secondary name node, data node, job tracker, task tracker, yarn resource manager, yarn node manager. These are the 7 processes that you will see once when the job gets executed or is under the execution, right? Now, once when a containment unit starts its execution, it launches the application, it launches the task tracker through the node manager containment, right? Once when the yarn child is created by the task tracker, the regular business of creation of the map task and the creation of the reduce task happens in the normal sequence as what we have seen in the previous setup, right? So once when all the application and running aspect is done, you can see that all the output and other allocated resources are returned back to the resource manager. So this is how the MapReduce 2.0 basically deals with the execution of job. You can see that the way in which the job executed in MapReduce 1.0 and the way in which the job is getting executed in a MapReduce 2.0 is completely different, right? The setup, whatever that is available, is completely different. Hence, you can see that there is a lot of change in the environmental aspects of the execution. Okay, and when you talk about MapReduce 3.0, which was recently released in 2019, the way in which the MapReduce 3.0 deals with it is completely different, because it has got more precision over the number of nodes that are being created, the number of containment units that are being created. It ensures that there are no failures in the system. So these are the different ways or anatomy of how job gets executed in MapReduce 1.0, MapReduce 2.0, and MapReduce 3.0. MapReduce 3.0 is not in an ambit of our course, but still it is very important that we understand the latest trends which are there in Hadoop system. So the key concept of Hadoop 2.0 is that the application is submitted to the framework, right? The container consists of basic 1 unit of execution, that is 1 CPU, and a containment unit consists of a memory or the storage of 2 GB. Now, this is at a fine-grained allocation of processes, right? When you talk about coarse-grained allocation, it is at the higher level of the yarn manager. So it replaces the fixed map and reduce slots which were there previously. The resource manager is responsible for global scheduling of resources, right? hierarchical queries are being maintained by the YARN resource manager. So the node manager is responsible for pre-mission agent. It is responsible for life cycle of the container, the container's resource monitoring. Application master is responsible for creating application master instance for every application. It manages the scheduling of task execution and example of MapReduce application master. So the limitation of MapReduce 1.0 was the maximum cluster size was equivalent to 4,000 nodes. The maximum task that could be created is equivalent to the number of nodes, which is 4,000. Course synchronization is done at the job tracker level. Right? That is the superficial way of management of jobs, including the resources. Everything was looked up by job tracker. Now, if there is a failure in a particular job, the limitation is that it used to kill all the jobs that is either running or either submitted in queue. Right? So the major disadvantage is the client has to resubmit the jobs every time when there is a failure that happens. Some more disadvantages is the restartability was very difficult. Given the fact that there is a failure that has happened in the Hadoop cluster, restarting the cluster would take a lot of time in MapReduce 1.0. And the utilization of resources was very poor. Support was only for MapReduce. It never supported any other systems above MapReduce. Right? For example, in MapReduce 2.0, we have support for Harp, Sharp, Spark, and other utilities which are used for processing the data for different systems. And it was not so great for graph-based processing applications. Lack of trust between the client and server. Right? The client and server should be on the same versions. If the client and server is on a different version, again there was a problem of compatibility issues. So the current system requirement for executing a program under the big data aspect is the availability, reliability, utilization, wire compatibility, agility and evolution, scalability up from 6,000 to 10,000 missions, with each missions having 16 cores, 48 GB RAM or 96 GB RAM, 24 TB to 36 TB disks. These are typical scalability requirements. 1 lakh plus concurrent tasks, 10,000 concurrent jobs. Right? These are some of the requirement. Right? If you take a small instance, very small instance of a Facebook data for sentiment analysis, these are the requirement for it to be executed. The Facebook data, what we can take can be a miniaturized version of it, which can be less than 1 GB, which can be appropriately somewhere around 100 GB plus, which is used for certain big data requirement. A full-scale big data analysis of a Facebook sentiment analysis data would be somewhere around 1 TB to 2 TB of data. Now, when you're processing 1 TB to 2 TB of data, the obvious expectation is that your machine should be capable with enhanced hardware capabilities, enhanced processing capabilities. So these are the requirement of it. Right? Whenever you say about any kind of analysis, the system should be first available 24/7. Right? For example, CDAC has got Garuda grid, right? Jatayu grids. Right? These are all grids which are available 24/7. Right? IBM has got its own grid. Right? Previously, I had shown from the Information Week example that it has created its own cluster for COVID-19 analysis. Right? Lot of proposals are all available wherein which you can apply if you have got an idea or a thought of how you can cut down or curb the COVID-19 problem. You can write a lot of proposals to central government. Even the state government VTO is allowing for a lot of proposals, right? So these are some of the cases wherein which you can make use of it, right? And second important thing is the utilization of data becomes very important. As and when we move ahead, as and when we go ahead, right? Consumption of data becomes very, very important. We keep consuming more amount of data for processing, right? And wire compatibility is a major issue. The wire compatibility should ensure that both the client as well as the server is on the same page. They are using the same versions, right? If the client is using 2.1, the server should also use 2.1, so that they're talking to each other in the same way. That is very, very important, right? The agility basically talks about the ability of the customer to control the upgrades to grid software stack, right? It's very important to know that every day as we speak, the hardware is getting changed, so as the software that is supporting for it is also getting changed, right? Whatever the was the software or the operating system that I used 10 years back is not the scenario today. Today's scenario is completely different, right? The software stacks needs to be completely upgraded every time, right? Majority of these rack servers or grids that we talk about, they run a version of the Linux flavor called CentOS, and this CentOS has a huge problem. The problem with the CentOS is every time there is a patch that is released for the server version of the CentOS, it needs to be patched with the places where it is being installed, right? The complete software stack needs to be upgraded every time, right? So this is my personal experience dealing with HPC missions, high performance cluster missions in my previous college, right? Where we initially started off with CentOS 6.1, but many of the application demanded it to be CentOS 6.4 and above, right? So we had to upgrade the entire cluster and reinstall the OS with a newer version of it. And this reinstallation is not as easy as what we do for your desktop machines or the laptop machines, right? It is very difficult. There are a lot of precautions that you have to basically take care before a new OS is being installed onto the HPC clusters, right? Now, what I would like to do is with this, I would like to stop for today's class, right? And we will meet tomorrow again with some more details.